derivative. So that's the solution. So the idea is this. We take the limit of a ratio, and both the top and the bottom independently go to infinity. So the limit as it goes to infinity of the ratio is the limit of their derivatives. Let's try it right now. So we have two functions. So the first function is e to the n. The next function is 3n squared. So let's take the limit. And by the way, you can take the limit of, it doesn't matter which one you put on top, which one you put on the bottom. Just interpret the results correctly. So if you take this, notice that top is definitely going to infinity, right? Bottom is definitely going to infinity. So we cannot determine what this ratio is going to go to. So what do? We take L'Hopital's rule. So we said equals, by L'Hopital's rule, the derivative of 3n squared, which is 6n, over the derivative of e to the n, which is e to the n. But they're still going to infinity. So guess what? L'Hopital's rule, again, when you take the derivative of 6n, it's 6, and e to the n, e to the n. You see why we like e to the n or e to the x? They're nice. Their derivatives are easy. So now, look what happens. Now, no longer is the top going to infinity, but the bottom is. Well, the bottom is going to infinity, while the top is standing still, the ratio goes to 0. And that tells us that f of n is strictly slower than e to the n. Strictly slower. Does that make sense? It is not proportional. Okay, so I'm going to tell you a few statements about big O, little o, omega, blah, blah, blah. You tell me true or false. Ready? Everybody likes true or false statements. Okay. F of n is an element of big O of g of n. True. It's the same rate or slower? Yup. Okay, f of n is an element of little o of g of n. True. Here's the tricky one. E to the n is an element of little omega of f of n. False. That's also true. Because little omega of g of n, go back on the tape. But what I'm trying to show, so basically, E of n, I'll try it again. G of n is an element of little omega of f of n. Is f of n is a strict lower bound for g of n? The answer is yes, because g of n is growing much faster. So therefore, f of n is a lower bound. And because it's a slower growing function, it's a strict lower bound. Is g of n an element of big omega of f of n also? Yes. Because it's the same or faster. Yes. How about this one? F of n is an element of theta of g of n. F of n is an element of theta of g of n. That is absolutely false. In fact, the only way you can say theta after solving the problem is when your limit goes to a constant. If your limit goes to a constant, it means that they are both proportionally approaching infinity. Therefore, nobody's winning. Top is not going to drive it to infinity, bottom is not going to drive it to 0. They're always going to be a constant away from each other. So what does that mean? Proportional. This is just a different example. Notice all I did here, instead of e to the n, I have 2 to the n with a derivative. Not a big deal. Okay, this one, we have n plus 5 log of n to the 5th power. Log of n to the 5th power. This is not log n, log n, log n, log n, log n. This is log n to the 5th. And many of you will say, hey, because 5, you can do that. So, take the limit of f over the limit of g. Rewrite it so that the exponent is in front of the log. So 5 log n. So this is the power rule for logs. Now, just in case you were wondering, if we have a limit, we can take the 5, which is a factor, and take it in front of the limit. We can do that. We don't have to do it, but we can. Nothing, we can do anything, only a factor. So, derivative of n plus 5. Now, L'Hopital's rule applied, infinity, infinity. So this is going to equal to 1, and the derivative of 5 log n is going to be 5 times 1 over n, which simplifies to n over 5. Now, clearly, as n goes to infinity, this goes to infinity, which means that which function goes faster? This function is faster. This is a slower growing function. So even though it's log n to the 5th, so for example, if n is 10, what's 10 to the 5th? 100,000. So log of 100,000, and this would be 15. So you might say, well, wait a second, which one is bigger? It doesn't matter which one is bigger now, because we're not looking at which one is bigger now, we're looking at the limit as these functions go to infinity. You may beat me now, says n plus 5, but I'll beat you later. As n goes to infinity, I'm going to be way above you, always. So this linear function is a higher complexity function than log n to the 5th. In fact, let me ask you a question. What if I change this 5 to a 25? N to the 25th power. Imagine 10 to the 25th power. Wow! That is a mega number, right? The answer is, what would happen to the limit? The answer is, the 5 would become a 25, the 25 would stay here, the 25 would stay here, the answer would still be the same. That means that even log n to the 25th power is slower growing as n goes to infinity than is n plus 5. But you probably figured something out. You probably thought, okay, but isn't it true that this log of n to the 25th power, isn't it going to be higher instruction count for a long time before it becomes a lower instruction count compared to this one? So what's happening is these two curves, so this first curve up here is way up here, and this linear one is kind of going like this. But then what's going on is this one's slowing down, and this one's going to take over. So there is a crossover point. How do we find this crossover point? How do we find this crossover point where the functions are the same, where their instruction count is the same, even though they have different complexities? Any idea? You know the idea, yeah. Same with each other. Just like we compared algorithms. When this is algorithm better than this algorithm. When this is less than this. When are these algorithms the same? And they're equal to each other. Same techniques. Okay, so you got that one. Let's look into a couple more. This is a good one because it uses n log n. N log n is a product. So you got to use the product rule. So the derivative of n log n is going to be n times the derivative of log n plus log n times the derivative of n, which is going to be n. So this is the original function. Now this is after L'Hopital's rule. This is going to be 2n plus 10. This is going to be natural log of n over n plus 1. Notice that they're still going to infinity. And so finally, when we simplify it, we get 0. That means that n log n grows more slowly than n squared. Even if we got rid of this, it's still more slowly than n squared. In fact, we don't really care about the 10n. Because when n is a million, this is a trillion, and this is 10 million. So this is just a very small thing. A trillion versus 10 million is like 10 million is nothing, right? It's like 1/1000 of it. Okay. And using logs, here's the interesting thing I wanted to show you. Let's take the log base 10 of n and natural log of n. Again, both of them are rising slowly towards infinity. Take the derivative of both. We have 1 over n here. 1 over n times natural log of 10. Dividing by 1 over n is like multiplying by n. The n's cancel. It's 1 over natural log of 10. Therefore, the limit of a constant is constant. actually, for any base, we can show that logs of any base, the limit as n goes to infinity, every log function over any other log function goes to a constant. What does that mean? It means that all log functions are proportional. So the last question is, are all exponential functions proportional? Let's take 3 to the n over 2 to the n. So the limit of 3 to the n over 2 to the n as n goes to infinity, they both go to infinity, but I can rewrite 3 to the n over 2 to the n as 3 over 2 raised to the power of n. 3 over 2 is 1.5. If you take 1.5 and you keep raising it to higher and higher powers, that ratio is going to go to what? It's going to go to infinity. So it shows you that exponential functions, even though they're inverse functions of logs, are not proportional to each other. Any value, any higher base value is a higher complexity. 3 to the n, higher complexity than 2 to the n. Log base 2, theta of log base k. What's k? Whatever you want it to be, whatever the legal base. All logs are proportional. Exponentials are never proportional with different bases. So where does e to the n fit in here? It's more complex than e to the n. Is more complex than what? E to the n. Where does e to the n fit in? What is e? 2.71828. 2.7. Okay, just remember that, please. 2.7. So where does e to the n fit in with its complexity? Is it faster than one of these functions? Which one? Is it slower than one of these functions? Okay, if I did a limit of e to the n over 3 to the n, what would that limit go to? It would go to 0. Why? Because 3 to the n is growing more quickly towards infinity than e to the n. So even our powerful e to the n function can be outdone by 3 to the n, n4 to the n, n5 to the n, etc., etc., etc. Okay. How's that? Okay, let's stop right here. So on Monday, our lovely GA back there, he's going to give us a short lecture on from the book. So if you want to look ahead, you're going to be talking about the second set of slides, nice and slow. He's going to cover a little bit of something called the master theorem, right?
Yeah.
And go over the homework.
Mm-hmm.
And then on